In this chapter, we will be exploring exponential functions. In this lesson, we'll be looking at how to solve simple exponential equations. And we'll begin by looking at how to change bases.
Okay, so there are a couple of things that you can do to help yourself solve exponential equations. Okay, and an exponential equation is one where the exponent is up in the, when the variable is in the exponent. So let's just take a quick look here. So here's a good example. 3 to the power of x is equal to 81. That's what we would call an exponential equation because the variable is in the exponent. That's typically the way you label equations, is by where you find the independent variable. If it's underneath the radical, it's a radical equation. Typically, if it's in the denominator, we call it a rational equation. So that's what we're going to do here. Now, our main tool at this point in time is going to be to convert all of the bases to the same number, if we can. Now, in this particular lesson, that's just going to happen. Okay, the specific equations that we're going to be looking at are going to be such that we will be able to take this, or to use this tool here. We're going to see later on in this chapter, we're going to look at another way of handling exponential equations when they don't work out quite so nicely. So right now our goal is to take every value in the equation and make it the same base. Change them all into powers of the same base here. Now to do that, let's practice, okay? So what we're going to do here is we're going to take a quick look at some expressions here. We're going to practice converting them to a given base here. So for example, 9 to the 2x, okay, is our power. What we want to do here is we want to alter the base. And then what we'll do is we'll fix the exponent to correspond to our new base here. So we want to make this base 3. So I would like this to be 3. Now the thing is, though, the base is 9. So what I need to do is I need to find some way of writing 9 as a power of 3. And it turns out that's just 3 squared. So this is 9. Okay, this is going to take the place of a 9. Now in this expression, what it is I'm doing here is raising 9 to the power of 2x. So this is 9 to the power of 2x. Okay, so there's my 9 to the 2x is now equal to 9 to the 2x. I really haven't done anything. Except now I've got a power of a power. And let's think back to some previous work that we've done. What do I do when I got a power of a power? I multiply the exponents. So this becomes 3 to the 2 multiplied by 2x, or 4x. So there we go. So 9 to the 2x is going to be exactly the same as 3 to the 4x. Because I really haven't done anything. 3 squared is still 9. Let's look at another one. 8 multiplied by 16 to the power of x. We want to convert this to an expression where everything is in terms of powers of 2. So I've got two factors here. 8 and 16. Now I can't factor an 8 out if that's what you're thinking. Okay, because first of all it's multiplication already. I'm not factoring out. You would factor something out of like an addition or subtraction. And secondly, I can't multiply the 8 by the 16 because there's this exponent here. Before I could get to the multiplication, I would have to do the exponent first, then the product. And I can't do that because I don't know what the exponent is. That's okay. So what we're going to do is we're going to rewrite both of these numbers here as powers of 2. Okay? So 8, let's just think about this. 8 is going to be the same as 2 cubed. Okay, 2 cubed is 8. Now I haven't done anything because again, 2 cubed is 8. Think about this for a second here. If 2 cubed is 8, 2 to the 4th is going to be 16. And again, I haven't done anything because 16 is 2 to the 4th. Right here, this factor, this 16 to the x, I need to keep that down here, so 2 to the 4, this has to be to the power of x there. So now I've got 2 cubed multiplied by 2 to the 4th to the x. Now I've still got to combine these things, and right now I can see how that's going to happen because I've got 2 powers of 2 multiplied together here. So 2 to the 4 to the x, this is a power of a power. So what I'm going to do is multiply those exponents together. Now I've got to deal with this first before I deal with the multiplication. That's order of operations, bed mass. Exponent comes before the multiplication. So this will be 2 cubed. There's my 8. And this will end up becoming 2 to the 4 times x. Now I've got 2 powers of 2 multiplied together. Let's think about that. What do? When I multiply powers, I add exponents. So this becomes 2 to the power of 3 plus 4x. Perfect, that's exactly what you do here. Now, this is an acceptable answer. There's nothing wrong with that. However, I suspect that there will even be people that are watching this that go, yeah, but I wouldn't write it like that. And I know, a lot of people, you would write it like this. You'd put that 4x first. And actually, that does look better. That's more of a formal way of writing it. And you'll see that there are benefits to following some of the formalities of mathematics. We'll see that in a little bit here. Let's keep going here. Keep practicing this. Okay, 81 to the x minus 2. Okay, 81. We're going to reduce, write this as a power of 3. So we know that this has got to be 3 to some exponent. Well, we know 3 squared is 9, and 9 squared is 81. So this must be 3 to the 4th. There's my 81. And then this will be to the exponent x minus 2. And now I've got a power of a power. I'm going to multiply the exponents here. Now you got to watch out for this. There's something that I call it, I call it a Timmy mistake in my class here. There's a type of question that you see often on exams where it says something like to the effect of like, Timmy is working through a problem, Timmy has made a mistake. And then you see all of Timmy's works, and the question is, where did Timmy make the first mistake? And you have to identify the step here. Well, this question right here is setting itself up for what I call a Timmy mistake, because what Timmy makes mistakes on is details. He gets big concepts. Timmy understands how to solve exponential equations, how to reduce exponential functions. What Timmy gets wrong are just little things here. For example, Timmy would tend to write this like this. He knows he's got to multiply the x minus 2 by the 4, but he would do this. He would go 3 to the 4x minus 2. You see, but that's not true. All he's done is taken that 4 and multiplied it by the x. He did not multiply it by that full exponent. You need to distribute the 4 to both of those terms in there. And so this should actually become 4x minus 8. That's the correct solution to that, or that's the correct representation. These two are identical. So please watch that, and don't make that little mistake there. It's a very, very predictable mistake. That's why that sort of mistake shows up on exams. Okay, 2 times 4 to the base 2. Once again, remember that we have to deal with this exponent here before we can deal with the multiplication, because exponent comes before multiplication in the order of operations. I'm going to convert these to base 2. 2 already is base 2. So I can just leave it like that. I would be wise, though, to write this very specifically as 2 to the 1, to bear in mind that that is a power of 2, and the exponent, when it's not written, is 1. I'm going to help myself out by doing that. 4 is going to be the same as 2 squared, and I don't think that comes as a surprise to anybody. You've been doing that one for a long time here. I haven't done anything. It's still the same basis here, except that this is 4 to the x, so I have to make this 4 to the x. Now, before I can deal with the multiplication, like I said before, I have to deal with the exponent here. So 2 squared to the x. I got to multiply those together, the exponents. So this becomes 2 to the 2x. And now I've got 2 powers of 2 multiplied together. What's the rule? Okay, the rule is I add the exponents. I'm helping myself out by putting a 1 there, because then I'll remember that, oh, this is going to be 2 to the 1 plus 2x. Again, if I can go back and refer to Timmy, when Timmy does this wrong, Timmy forgets to put the 1 there because he doesn't see it as he goes down. He knows that it's there, but he doesn't see it in the expression, and so he forgets to deal with it when he does the simplifying here. And although this is a correct answer, I know a lot of you would say, no, don't write it like that. Write it like that. That's the stuff. Yeah, that looks better. So 2 to the 2x plus 1. Sorry, my pencil lead just broke there. There we go. Good. Okay, let's keep going. Let's do just a couple more here. We're going to let them get a little bit more involved. But what you're seeing here, by the way, as we flip through these examples, these are the numbers that you will stereotypically see in these questions. Okay, the 9, 8, 16, 81, 4, like these are all really, really common. We don't stray much from these bases here. So this guy here is similar to the last 2 that we've looked at here. It's got a binomial in the exponent, and I told you there's a place right there where Timmy makes mistakes. Okay, there's a little detail there. Okay, then we've got this 9 here. We got to multiply them together. We got to deal with this first and multiply them together. So there's just a couple of things going on here. So first of all, 9 is 3 squared. Okay, 27, I'm going to play with that a little bit, but that's going to be 3 cubed. And so it's 27 to the x minus 1. So it'll be 3 cubed to the x minus 1. As with the previous questions that we've looked at that have been similar to this, when I've got a power of a power, I got to deal with that first. I got to deal with the exponent here before I deal with the multiplication between the powers. So the 9, the 3 squared stays, that's fine. And this is going to become 3 to the 3x minus 3. You have to distribute the 3 through to both of the terms in the exponent. Once I've done that, now I'm going to multiply the two powers together. And how do I do that? I multiply powers by adding the exponents. So this is going to become 3. Now when I add the exponents, I have to concern myself with like terms here. There's nothing like about the x, okay? But there is between the 2 and the negative 3. So this becomes 3 to the power 3x. And that's going to become minus 1 because the 2 and the negative 3. So there we go, 3 to the 3x minus 1. And this representation here is identical to this one up here. Okay, good. And finally, this guy right here. Oh boy. Well, we had to do something like this. There had to be something like this in this expression here, in this little section here. One where we're seeing a reciprocal here. Okay, first of all, I want to convert this to base 4. The first thing I'm going to do is I'm going to jump on that 16 here. I know that 16 is going to be 4 squared. Okay, great. Now this right now, this still isn't a base 4. This isn't a base 4. Oh, sorry, the 16 I converted to a base 4, but this whole expression isn't a base 4. Every other question that I've just done, when it said convert it to a base 3, my final answer was a power of 3. See, this isn't. This right now is still a power of 1 over 16. So I can make this a base 4 by bringing this up to the new... Oh, sorry, did I say 1 over 16? I meant 1 over 16 if I didn't say that. I'm going to bring the 4 up into the numerator by making this 4 to the negative 2, and then that's still to the 4 minus x. Now this is still 1/16, but now it's written as a power with a base of 4. Okay, here the base here was not 4, it was 1 over 16. Here it's 4, and then now the exponent's got the negative 2. So basically the change that I've made here has been in the base and the exponent. They've kind of balanced each other out here. Now I've got a power of a power, and I know based on a bunch of experience that I will multiply that out. Again, don't make that Timmy mistake. Make sure you distribute that through. So this will become negative 8, positive 2x. And then, yeah, we're not going to leave it like that because we know that most people are going to say, no, 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 that looks better. Good. That's the answer I'm looking for, 4 to the 2x minus 8. So that's what we mean by changing the bases here. So you want to get good at this. Okay, there will be some practice in a little while here, but you want to get good at that because for a certain type of exponential equation, this is how you're going to solve it. Okay, and I am going to show you another method for solving exponential equations for sure. But when you can see this kind of a method working in a question, this is way, way quicker.
In this next section, we'll apply what we've just looked at to help us solve equations.
Okay, before we get into actually solving equations here, I want to just give you just a very brief little set of steps here. Okay, this is how you're going to do it if you see it. So first of all, what we're going to do is we're going to rewrite, okay, in terms, rewrite in terms of a single base. You're going to rewrite everything in terms of a single base. So as long as you can see all these numbers being powers of 2, powers of 3, we're going to rewrite every one of those powers as a single base here. What we're going to do is we're going to combine and simplify both sides. And what I mean by that is essentially what we want here at the end of that step here, we should have power equal to power. That's the goal here. You want to have a power equal to power. But because of the first step, when this has been done, you'll have power equal to power, but note the base is going to equal the base. Because we've already done that. We've taken care of the fact that the bases are the same. We've made the bases the same in the first step. In the second step, we've made power equal to power. And so the very last thing that we're going to do here is we're therefore going to state it like this. If the powers are equal, if the bases are equal, we can conclude that the exponent is equal to the exponent. And then solve typically for x, or for the variable. Okay, for whatever the variable is. So these are our steps here. Rewrite everything in terms of that single base that you see as being common to every power. Combine and simplify both sides of the equation. And what we want to be left with is power equal to power. This should now be a situation where you've got power equal to power where the bases are the same. And that means if everything is equal, the exponents must be equal. And that's where I'm going to do the work to actually do the solving. So now we're going to take a look at several examples of exactly how this works.
Solve for x in each of the following. 3 to the x equals 81.
All right, well, it's fitting that we start with this one right here. This was the example equation that we used when we discussed or defined what an exponential equation was. 3 to the x is equal to 81. Now, based on the work that we did in one of the previous examples here, we already know that 81 can be rewritten as a power of 3. So I'm not going to do anything to the left-hand side because it's already a power of 3, but I can change 81 to become 3 to the 4. Now, because power is equal to power, and the bases, because think about this, there's two parts to a power. There's the base and the exponent. If I am stating that the powers, the whole powers are the same, and I can see that the bases are same, I can conclude that the exponents must be equal. So x must be the same as 4. X is 4. That's the logic in solving exponential equations in this method.
2 to the x is equal to root 2.
Okay, so this question right here, again, I've got this power equal to, a very clear power with a simple base equal to another term here. What I got to do is rewrite this as a power of 2. So I can see that the bases are going to be 2 here. All I got to remember here is what that radical means as an exponent. Okay, and this is one of the rules that we've looked at in the previous lesson here. This will become 2 to the 1/2. That's what we mean by the square root. And so now I've got power equal to power. The base is the same. That means the exponents. Okay, so therefore, that's what the little dots mean there. Therefore, x is equal to 1/2. That exponent must be equal to that exponent, which simplifies down to x equals 1/2.
7 to the x minus 2 is equal to 343.
Okay, now here's a question that's going to require just a little bit more effort. This will be a little bit more of an example of what you might see on an exam or on a quiz or something like that. Again, I need these to be the same power. That's my goal here. Now, already on the left-hand side here, 7 to the x minus 2. 7 is about as simple as I can make that. I mean, it's a prime number. That's good here. 343, I am guessing, can be written as a power of 7. Can't do much with the left-hand side. There's 7 to the x minus 2. But 343, well, let's just think about that. 7 squared is 49. 49 times 7, 49 times 7, there's my 343. There it is. So 7 cubed. 7 as a factor 3 times gives me 343. Good. So now I've got power equal to power. Base is equal to base. From that, I conclude that my exponents must be equal. It must be the case that x minus 2 is equal to 3. I am not canceling the bases, by the way. There's no such thing as canceling the bases. There's no process of simplification that does that. All I'm doing here is saying that if they're equal, and if the bases are equal, exponents must be equal. But now this gets me a little equation that I can solve by simply moving the 2 over, and I get that x is equal to, add 2 to both sides, x is equal to 5. And so, there's my solution.
2 to the 4x is equal to 4 to the x plus 2.
All right, you can probably see here how the equations are starting to get just a little bit more complicated. We're kind of baby stepping into some more complicated work here. Look at the bases. Ignore the exponents right now. Doesn't matter. Look at the bases. I've got 2 and 4 here. The common base is going to be 2. So I don't really need to do anything to the left-hand side. That one's good. But the 4 needs to be rewritten as 2 squared. Now notice I haven't done anything. 2 squared is 4. This is still 4 to the x plus 2. So in my next step here, what I'm going to do here is deal with the fact that I've got a power now of a power. So the left-hand side still is, there's nothing I can do there. There's nothing I need to do there. But the right-hand side, I need to multiply the exponents. And remember, don't make that Timmy mistake that I mentioned before. Remember how Timmy forgets the little details here. 2 has to distribute to both of those terms in the binomial exponent there. So 2 to the 2x plus 4. And now this is exactly where I want it to be. I've got power equal to power. I've made sure that the bases are the same. So I can conclude that the exponents must be the same. So now I've got this linear equation, and you've been solving these for a couple of years already. How do I get x by itself? Well, what I'm going to do is I'm going to bring it over to one side. So I'll bring it over to the left-hand side by subtracting 2x from both sides. So 4x, and I subtract the 2x. There we go. And now 2 multiplied by x equals 4. So to figure out that is I'll divide both sides by 2. X is equal to 2. So there's my final solution to this problem.
2 to the x minus 1 is equal to 4 to the x minus 2.
All right, now this question is just slightly more involved than the previous question, simply because we've got binomial exponents on both sides here. Again, when I look at the bases though, I can see that the common base is going to be 2. So 4 can be rewritten as 2 squared, and this is still 4 to the x minus 2, so it'll be 4 here, again, to the x minus 2. Power of a power means I'm going to multiply the exponents out, and again, I'm careful to distribute. 2x minus 4. This is exactly where I want it. Okay, bases are the same, powers are equal, power equals power, which means therefore that the exponents must be the same. And I'll bring this x over to this side here, because if I subtract x from both sides, I'll be left with a positive x on the right. And I'll add 4 to both sides, and we'll get 3. So there we go. There's our answer. X is equivalent to 3.
3 to the 5x minus 1 is equal to 81 to the 3x.
Okay, here we go. Power equals power. Again, looking at the numbers here, looking at the bases, I can see 3 is as simple as it's going to get. But 81 is itself a power of 3, and we've already played with this a couple of times. That's going to be 3 to the 4th. Okay, so now this is 81, so to keep the expression the same here, 81 to the 3x, I take 81 to the 3x. Nothing had to happen on the left-hand side, but on the right I've got now a power of a power, so this becomes 3 to the 12x when you multiply those together. This is what I've wanted. Power equals power, bases are the same, so I know that 5x minus 1 must equal 12x. And for simplicity's sake here, I'll subtract 5x from both sides, and this will become negative 1 will equal 7x, and then divide. Now I'm getting a fraction as my result, but that's okay. Nothing wrong with that at all. The answer is negative 1/7.
3 to the x is equal to 27 times 3 to the 2x.
Now in this question, the difficulty gets increased here because we've added another factor. Now, but looking at those, you can see pretty quickly that these are all powers of 3. So 27 is itself 3 cubed, so that's just 27. And then I've got 3 to the 2x. Okay, now I got to simplify that right-hand side, because what I want is I want power equal to power. That's my goal here. So now, notice there's nothing to simplify in terms of the exponents here, because this is, for the individual factors, because this is the exponent on 3, this is the exponent on 3, but on the right-hand side, when I multiply 2 powers of 3 together, I add the exponent. So this will become 3 to the 3 plus 2x. Okay, now, that's probably as far as I need to take it, because at this point here, I've got power equal to power, bases are the same, so the exponents are going to be the same. Maybe I bring the x over, subtract it from both sides, so that'll be an x there, and I'll subtract 3 from both sides to get that x is equal to negative 3. And there I go. That was my goal. I'm done.
2 to the 5x plus 2 is equal to 2 to the 17.
All right, now this question is hopefully not so straightforward that people don't see what's going on here. I already have power equal to power, and the bases are the same. So I can immediately state that the exponents must be the same. And so if 5x plus 2 is equal to 17, I can subtract 2 from both sides and get that 5x is equal to 15. And by a quick little division there, I'll get that x is equal to 3.
9 to the x plus 1 is equal to 1.
Okay, now this question here is a little bit of a trap. Okay, I admit that freely here. We're going to catch a lot of people with a question like this because they're going to be looking for the wrong thing here. You're going to try to make 9 some sort of power of 1, and it just isn't. It's just not a power of 1. However, 1 is a power of 9 if you remember all of the rules properly. Okay, what power of 9 gets you 1? Well, the answer is 0. 9 to the exponent 0 is equal to 1. And now I've got power equal to power. The bases are the same, so I can state that the exponents must be the same. And then bring the 1 over, and I'll get that x is equal to negative 1. Okay, now, don't let this question or a question like this throw you off. Please keep that in your mind here, that anything to the exponent 0 is going to be equivalent to 1, okay? It'd be a shame to lose marks on something. This is the kind of question where if you got it wrong in the exam, you'd look back at it and go, oh, what was I thinking? Okay, so just be careful. Be very deliberate with your work here, that you don't make a mistake with that.
5 to the 4a plus 2 is equal to 25 to the a.
Okay, here we go. This is a different value here together. We haven't really worked a lot with 5s, but I hope you see right away here that between these two numbers here, the common base here is 5. This left-hand side is 5 to the 4a plus 2. That's not a big deal. But 25 is going to be the same as 5 squared. And then this is still the same thing. This is 25 to the a. This is still 25 to the power of a. I've got a power of a power on the right-hand side, so I need to simplify that first before I do anything else. And this will become 5 to the 2a. And once I've got it as power equal to power, bases are the same, just like before, I can state that the exponents are the same. And now maybe bring the 2a over to the left-hand side, so subtract it from both sides. And then maybe bring the 2 over by subtracting 2 from both sides. So I get 2a is equal to negative 2. Dividing both sides by 2, you get a is equal to negative 1. So there we go.
5 times 2 to the x minus 1 is equal to 40.
All right, now this question here, it's got a little bit more to it. Now, look at this power right here. Just ignore everything else here. Look at that power, 2 to the x minus 1. That suggests to me that the common base here is going to be 2. But 5 is not a power of 2, but neither is 40. So what I need to do here is kind of simplify this down a little bit here. What I should do first is isolate that power by dividing both sides by 5. Get rid of the 5. And when I do that, I get 2 to the x... Whoops, sorry. I don't know why I turned that into a positive. It says 2 to the x minus 1 is going to equal 8. Oh, well now, yeah. Now, I do see the powers of 2 here. The left-hand side will be 2 to the x minus 1. The right-hand side will be 2 cubed. That's 8. And now that I've got power equal to power, bases are the same, I know that the exponents must be the same. And then to isolate the x, I would add 1 to both sides, and I will get that x is equal to 4. There's my solution. So when you see something like that, when you get a question here and you're like, okay, how do I solve this? How do I get everything to the same base here, especially when it doesn't look like they're the same base? Consider isolating one of those powers first, because there's probably a number with that same base hidden somewhere in that question that you gotta look for.
Now we'll take a few moments to look at how you might use your calculator to help you solve the same equations. Solve for x in the equation 5 to the x plus 2 is equal to the square root of 125.
Okay, now that we've taken a look at how to do this algebraically, we're going to take a quick look at a calculator solution here. So let's say that this was the question. Solve for x in the following. We have 5 to the x plus 2 equals the square root of 125. So algebraically what we would do here is we have 5 to the x plus 2. 5 is a prime number, so I already know that that must be the base that I'm looking for here. So 125 must be some power of 5. The root of 125 is 125 to the 1/2. And then 125 is 5 cubed. So then we end up writing this as 5 to the x plus 2 is equal to 5 to the 3/2. My bases are the same and the powers are the same, so I can conclude that the exponents must be the same. Okay, and if I simply subtract the 2 from both sides, I get that x is equal to negative 1/2. Now, let's verify that. Let's go to our calculator and see that we get the same thing here. And one way of doing this, and there are others here, but there's one way of doing this, is to take both sides of the original equation and graph them, and then look for the point of intersection. So here we go. So here's my calculator here, and I've got 5 to the power of x plus 2. Whoops, sorry, there's a little bit of a shine there. I'll just tilt it here. And then this will be the square root of 125. Okay, so 5 to the x plus 2, and then the square root of 125, and I'll graph that. So you can sort of see the blue line there. It goes, there's my power of 5 here. And now I'm not seeing anything, and I can tell the calculator's done thinking here, but I didn't see another line here. So my two graphs here were 5 to the x plus 2 and the square root of 125 here. Oh, see, now I see the problem. 125 is bigger than 100. The square root of 100 is 10. Now my window settings go up to a maximum of 10. I need to make that a little bit bigger. I need to make my y max a little bigger. Let's just say 15. I don't know how much bigger it's got to be, but 15 I would think would work. Ah, here we go. There's my square root. Oh, and that's where they meet. Okay, and that line keeps going. So now to find the point of intersection, I will press second trace to get into that calc menu. That's what I'm trying to access. I'm looking for number 5, the intersection feature. And then what I'm going to do here is, the question is asking me, am I on the first curve, am I on the second curve? What I'm going to do is just move my cursor so it's relatively close to the point of intersection. There are only 2 curves here. The question's asking, the calculator's asking, am I on the first curve? You press enter, yes. The calculator immediately jumps into the other curve. Is this the second curve? Press enter for yes. And the calculator's going to ask you for a guess. The guess is basically just the calculator's way of trying to get to the answer faster. So just press enter, doesn't matter. And then there we go. X is equal to negative 0.5. Okay. Now something you should know about what the calculator has done here, and I'll just show you this real quickly because this is interesting here. But that is the answer we found algebraically. But just to verify that, let's quit. Once you've quit, if you press X and press enter, the calculator remembered what it just found. It remembers that point of intersection. And now, if I press my math button right there, one of the very first options I get is convert to fraction. I can choose that, and then it'll convert that answer to negative 1/2. Like, that's exactly what I got. That's how I wrote it on the sheet there. So just a little bit of a kind of a review of some of the tools you've got on the calculator to help you answer these problems.
Which graph below shows the solution to the equation 5 to the 2x plus 1 is equal to 1 over 5 to the x plus 2?
So in this case, to help us answer this particular problem here, I mean, we're supposed to see, like, graphically what's going on. Notice that in every case here, we've got 2 different graphs for every one of these. So I think this links back to the previous question. We just have to graph both sides of this equation. So here we go. Let's go to our y equals, okay? And I'll enter this as 5 to the x plus 2 5 to the, what was it, 2x plus 1? Yeah. 5 to the exponent, 2x plus 1. And our next one there was 1/5 to the x plus 2. Now I got to make sure I put that 1/5 in parentheses there. Okay, 1/5 to the x plus 2. Because I got to make sure that the calculator understands that I mean the entire fraction there, 1/5. Now, if I look at my graph here, look at the window settings, because I'm kind of lazy. I want it to look sort of like what I've got here. In almost every case here, we're only going a little ways to the left and the right here. Maybe I'll make my x here, let's say negative 3, comma 3, whoops, going up by 1. And we'll make our y here, y min, well, my y mins go down to negative 6. I'll go down to negative 4 and up to, let's say positive 4. Basically, I'm just trying to average or compromise between all 4 of those graphs here. Just press graph and see what happens here. Okay, so the 1 is dropping down, swooping, and they're matching right there. They're kind of swooping in opposite directions from each other. Okay, so which one of these graphs sort of looks like that? Oh, there it is. The answer is C. Now, by the way, I can't help it here. Let's go a little bit further and let's solve this. How do you get the solution of this equation here. Once you've got it graphed, you press second trace, go down to intersect, and then we're going to move the cursor close to that point of intersection. It doesn't have to be right on. So I'm going to stop a little ways over here just to show you this. It doesn't have to be on here. Calculator asks, am I on the first curve? Press enter. You should see it jump immediately down to the second curve. Calculator asks, is this actually the second curve? Yes. And it says, is it okay if I guess this? Sure, press enter. And we get an answer of -1. And that's how you'd use a calculator to help you solve that question.